All right, let's talk about one of the absolute cornerstones of machine learning, linear regression. It's a super powerful way to find patterns in data and even predict the future. And we're going to start with a really simple question that pretty much any business on the planet would ask.
So let's say you're running a company. You're spending money on TV ads. You're pouring cash into social media, but how do you know if it's working? More importantly, how can you predict next month's sales based on what you plan to spend? This is the exact kind of problem linear regression was born to solve. And the tool for the job? You guessed it, linear regression. It's a type of supervised learning, which is just a fancy way of saying we teach the machine by showing it a bunch of real-world examples. At its heart, it's all about finding a simple, straight-line connection between your inputs, like your ad budget, and your output, in this case, sales. Now, we could start simple. We could look at just one thing, like TV ad spending, and see how that predicts sales. That's called simple linear regression. But let's be honest, the real world is messy, right? You're probably juggling TVs, social media, newspaper ads, the whole shebang. That's multiple linear regression, and it's what you're going to see out in the wild almost every single time.
So what does this prediction line actually look like? Well, this might give you flashbacks to high school math class, but it's literally just the equation for a line. Think of it like this. Your final sales are going to be some baseline number, plus a little boost from your TV ads, plus another boost from social media, and so on.
The real magic here is in those boosts, which we call coefficients. These are the numbers that control the angle, or the slope, of our line. If you pick good coefficients, your line will slice right through the heart of your data points, making great predictions. Pick bad ones, and your line will be totally useless, just floating off in space.
The other piece of the puzzle is the bias, or the intercept. Just think of it this way. What would your sales be if you spent zero, absolutely nothing on advertising? That's your bias. It's the starting point. And changing it is like grabbing that whole prediction line and just shifting it up or down the chart. Okay, so we've got a recipe for a line. It has a slope and a starting point. But wait, there's a problem. A big one. You could draw an infinite number of lines through that data. So how in the world do we find the one that's actually the best? How does the machine know? Simple. We measure how wrong it is. We call this the error. For every single sale that actually happened, we look at what our line predicted would happen. The gap between those two numbers, reality and prediction, that's our error. Let's make this real. Check out this table. In the first row, our actual sales were 2,000. Our line predicted 2,100, so we were off by negative 100. We do the same thing for the next row. We were off by negative 100 again. And we just keep doing that for every single data point we have. All right, so now we have a whole list of individual errors. I mean, the obvious next step is to just add them all up to get the total wrongness of our line, right? Seems logical. So we take our minus 100, add another minus 100, then add a positive 100, and one more positive 100. What do you think we get? Zero. Zilch. The total error is zero. But hold on a second. That can't be right. If our total error is zero, that should mean our model is absolutely perfect. But just look at the table again. We were wrong on every single prediction. So how is this possible? What is going on here? And that's the trap. The positive errors and the negative errors perfectly canceled each other out. It gives us this totally fake sense of confidence that our line is perfect when it's not. So the solution is simple. We have to find a way to make all the errors positive. We don't care about the direction. We just care about how far off we were. So how do we pull that off? Well, there's a really clever 4-step recipe. First, you calculate the error for each point, just like before. Second, and this is the genius part, you square every single one of those errors. A negative number squared becomes positive, right? Problem solved. Third, you find the average of all those new squared numbers. We call that the mean squared error, or MSE. And finally, you take the square root of that whole thing, which just brings the number back to a scale we can actually understand, like dollars instead of dollars squared. And what you're left with is the gold standard, the root mean square error, or RMSE. This single number is our North Star. It's an honest, reliable metric that tells you, on average, how far off your predictions are from reality. So if your RMSE is 10, it means your predictions are typically off by about $10. Super useful. Okay, let's take a breath. We have our line, we understand its parts, and we have a rock-solid way to measure how wrong it is using RMSE. So that brings us to the biggest question of all. What are we actually doing when we say we're training one of these models?
The goal is actually really simple. It's just to find that one magical combination of coefficients and bias that produces the absolute lowest RMSE you can get. That's what the computer does. It tries a line, measures the error, adjusts the line a little, and measures again, over and over, thousands of times, until it finds the best possible fit. That whole process, that hunt for the lowest error, that's the learning in machine learning.
And this whole idea really gets at the core philosophy of data science. You're never, ever going to build a model that's perfectly right all the time. The world is just too complicated. The real goal isn't to be perfect. The goal is to be the least wrong. And with a solid metric like RMSE, we have a compass that's always pointing us in the right direction.